Welcome to this tutorial on CIVA Education Eddy Current Testing module. The goal of this tutorial is to help you familiarize yourself with CIVA Education modeling software. In the Eddy Current module of CIVA Education, three tools are proposed: probe response, field computation, and inspection simulation. Let's open the probe response module with a planar default configuration. With the probe response module, you can compute the impedance diagram as a function of the frequency and the lift-off signal. Open the Specimen panel. In the Geometry tab, you can define planar or cylindrical geometries. Go on with the planar component and modify the thickness to 5 mm. You can define another material. For instance, you can select aluminum from the materials database. In the Probe panel, you can define the eddy current sensor. For instance, modify the dimensions as shown here. You can also adjust the lift-off value to 0.1 mm in the Position tab. At the top of the Probe Response panel, keep frequency as the variable parameter. By selecting a minimum value of 1 kHz, a maximum of 1 MHz, 25 values and a log scale, the variation range is defined. Now let's run the computation. In the first analysis window that opens, the normalized impedance diagram is displayed. It is available with an impedance plane view or with separate graphs for the real and the imaginary parts. With the mouse and the control button, you can zoom in and adjust the scale to better analyze the impedance diagram. Cursors help you navigate within the frequency range. Values are displayed in the toolbox at the bottom. In the other dataset, the same types of results are displayed but directly in ohms. Back in the Model tab and the Probe Response panel, you can now select the lift-off as the variable parameter. Define the operating frequency, for instance 300 kHz. Adjust the variation range and the number of lift-off values and run the calculation. The most relevant page to display for the lift-off signal is the raw value in ohms in the dataset specimen. To evaluate the phase of the lift-off signal, it is necessary to balance the results at the lift-off minimal position. Enable the balancing tools from the toolbar at the top. Put both cursors at the minimal lift-off value and activate the balancing. You can now estimate the phase angle at the lift-off signal from the toolbox. From the desk, you can now switch to the field computation module while keeping the current configuration. By doing so, the specimen and probe remain the same. In the acquisition panel, set the operating frequency to 50 kHz. Then, adjust the field computation zone's dimensions and sampling and position it in the component section just below the probe's center. Other orientations of this calculation area could be possible. Run the simulation. Different physical quantities are available in the results. Open, for instance, the eddy current density map. The analysis page includes the 3D view, a section view with cursors, and two profiles showing the eddy current density in the component versus a horizontal axis and a vertical axis. Back in the Model panel, you can modify the sensor's dimensions to simulate a larger coil. You can also add a ferrite core. Then run the simulation. Now, in the desk, let's switch to the Inspection Simulation module and select the default configuration on a tube. Keep the specimen as it is regarding its dimensions and material properties. A flow panel will let you define a defect, which can be a groove or a hole. Let's define a flat bottom hole of 0.5 mm depth, 0.8 diameter, located on the outer wall. In the probe panel, add a second axial coil similar to the first one and adjust its distance from the first coil. In the acquisition panel, keep the default frequency of 300 kHz. You can observe in the table that both coils are drivers and receivers, and that -1 set for one of the coils in the reception column will define a differential acquisition mode. Finally, you can check in the inspection panel that the probe starting position and the scanning length are relevant to cover the zone to inspect around the flow. Let's run the computation now. An impedance plane view and a real imaginary parts graph are available. From the CIVA Manager, you can display the 3D view through a simple drag and drop. The coil's position in the 3D view is interactive. It is refreshed when you move the cursor. You can even grab the coils with the mouse in the 3D view by pressing the control button. In the toolbox, the results are available: amplitude, phase. You can also automatically compute the maximum signal value thanks to the peak-to-peak icon in the toolbar. In the Measurements tab, you can select a differential measurement mode adapted to this probe and see the results. The toolbox also includes calibration tools to amplify the signal value and to rotate the phase. From the desk, let's define one last case by selecting a default configuration on a planar component. On these components, different notch length can be selected. Select a 2 mm long, 1 mm high surface breaking flow. Add a second coil and adjust its distance from the first one. In the acquisition panel, you can modify the input current and reception coefficients so that one coil will be the driver and the other one will be the receiver. It is a driver pickup acquisition mode. From the inspection panel, or directly by double-clicking on the sensors, you can modify the start position of the scanning. Then, adjust the number of steps to cover a large enough area. You can run the simulations. Then you can analyze the results. Thank you for watching this video. If you want more information, please visit our website or contact us at contact@extend.com.